So in chapter 1, we talked about energy conservation. And we saw the limitation that energy conservation being very useful information, but it does not tell us anything about how fast or how slow things are happening. So that brings us to chapter 2, which is going to give us this rate information. How fast do things happen? How slow do these things happen? And what are the mechanisms? How exactly does the energy transfer take place? So the contents of this chapter follows pretty much what we see in high school: conduction, convection, radiation. Hopefully we'll do more than what we do in high school normally. And we would get into some rate laws, some little equations that give rates of heat transfer. And these will relate the rate of heat transfer to temperature. So first, conduction. So before we get to the law for heat conduction, it is useful to define two things. One is flux and the other is flow. So let's say a body is releasing 100 watts from its surface. So the heat flow from the body to the surroundings is 100 watts or 100 joules per second. That's the flow. So this is flow is equal to 100. Suppose the body surface area, which by the way is the typical body surface area for an average human being, if there is any such thing, for that area, then this 100 watts, if it is equally distributed over all the surface, then how much of that energy is coming out per unit area? So flux is flow per unit area. And so it's 100 watts divided by 1.4 meter square, which gives me 70 watts per meter square. So flux is 70 watts per meter square. You notice that flow is in watts and flux is watts per meter square per unit area. We can't forget about these two things. So this slide has to do with mechanisms of conduction heat transfer. So on the left, we have cartoon for a solid, and on this corner, we have a molecule at higher temperature. Now, higher temperature means more energy. So in a solid, the molecules are sort of connected by a lattice, and higher temperature means higher energy, so this vibrates more, and that makes the next one vibrate, and that makes the next one vibrate. And so in this way, energy from higher uh, temperature molecule is transferred to energy of a lower temperature molecule in a very orderly fashion, because they are all connected in a lattice. So this is the process of heat conduction. Because they are connected, the energy is moving by sort of touching, and so energy moves from higher temperature to the lower temperature by conduction. In a gas, on the other hand, the situation is slightly different in conduction. So let's look at these red molecules in a gas, which are hotter, so they have more energy, where the blue ones have less energy. Now, as the red collides with the blue, it transfers energy to the blue molecule. Now, if you think of this imaginary line here, then and if you think of how many molecules are how many of the red molecules are crossing this line, then there is more of the red molecules crossing this way than crossing the other way. Remember, the movement is random, so the red molecules can go through it to the top or to the other in the other direction. But there will be more going toward the top than going the other direction. Why? Simply because there is more of the red ones in the lower side. But in this process, because the reds have higher energy, then energy is being transferred from the top to, from the bottom to the top. And so this is the process of heat conduction in a gas. In a liquid, it is not as random as in a gas, but also not as structured as in a liquid, so it's somewhere intermediate situation. And one thing I want you to see, that these molecular movements that we are showing here, these are at the molecular level. So when we study convection in just a few minutes, that's not this kind of movement. That's bulk flow added on top of this. More will be explained later.
Okay, we know the qualitative nature of heat conduction, but we still do not have a formula that says how the rate of heat conduction relates to things like temperature. And that's what we're about to do. So let's look at a slab that has a hot side and a cold side. And let's look at the temperature profile along this x direction like we have here. So the temperature profile can look something like this, from hot to cold along the x-axis. Now the heat flux, and we have already defined flux. So heat flux in the x direction in watts per meter square at a position x is q double prime at x. That is proportional to the slope of this temperature time curve dt dx. This is the rate law for conductive heat transfer, known as the Fourier's law. Okay, so heat flux is proportional to the temperature gradient. Heat flux at any location x is proportional to temperature gradient at that location. Now, this is again looking at it very generally, it's like the rate at which the stuff is flowing is proportional to the driving force. Here the driving force is the temperature gradient. The proportionality constant can be written in terms of an equality, and then we get the proportionality constant as K. It is this K, the proportionality constant, that we will be calling thermal conductivity. Now, the reason we have a negative sign, we are going to explain that in a moment. But for now, heat flux is equal to thermal conductivity times temperature gradient. Again, this is the Fourier's law. If that is flux, then the flow, which is the amount of heat that flows over the entire area. So in this case, for example, the heat flowing over the entire area would be given by the flux formula that we have here multiplied by the area. The flux here, watts per meter square, is the amount of heat that is flowing in this direction per unit area, whereas this one, Qx, is over the entire area. Now about the negative sign in the Fourier's law. You notice one thing, that in Fourier's law, a dt dx in this example is negative because temperature is dropping this way. So dt dx is negative. So if I wrote qx double prime equal to k dt dx, we know dt dx is negative and this k is positive, so which means I'm going to get a heat flux value that is negative. But look, temperature is high here and low here, so thermodynamically we know that heat has to go this way, so the heat flux in the x direction has to be positive in this case. So to make the formula consistent with the physics, ensuring that it obeys the law of thermodynamics, we put in a negative sign. Now the negative and negative would make it a positive sign for heat flow, which makes sense. If it is hot here and cold here, then heat should flow in this direction, and the formula will also give a positive quantity. So it's now consistent. So just a little digression about how these laws, so to say, come about. So many of you have heard of Murphy's laws, law of final exam. Okay, and there are more. Second law of final exam. So how did they become laws? It's because something was observed and then it sort of seemed to get repeated enough time. So eventually we kind of make fun of it and call these as laws. But the Fourier's law that you saw, that also started from some practical observation in a very specific situation for a given material, for a particular temperature gradient, and so on. But then over time it was seen to apply to many different materials and many different situations. Then even later we could give some theoretical proofs to that relation. So then it became accepted as a law. We're going to do an extremely simple problem that just basically uses the Fourier's law that we just wrote. We're just plugging in numbers, but we try to use the law in a very specific situation. So we want to calculate the rate of conductive heat transfer between 2 points. So think of a slab. This is a slab of either skin plus subcutaneous fat or muscle with two different thermal conductivity. But we always maintain the same temperatures on the two ends. Okay, so we know the temperatures and we know the K, and we know the thickness, of course. And using Fourier's law, we want to calculate the rate of heat conduction. So for skin plus fat, we use the Fourier's law, which is minus k del t del x. Now this time as we will show later, under some specific situation, like a steady state in a slab, the temperature profile is linear. If temperature profile is linear, then there's only one slope. So del T del X is basically change in temperature between these 2 points and divided by the change in distance. So I could write minus K del T del X, and if I plug in number, 0.28 watts per meter per degrees Kelvin is the thermal conductivity. This is the unit for thermal conductivity, watts per meter per degrees Kelvin. Then delta T is change in temperature. So if this is my positive x direction, then I take the point ahead minus the point behind. So 5 minus 20 divided by the thickness, 50. 50 times 10 to the minus 3 meter. Okay, so if I do that, I get 373 watts per meter square. What does this mean? This means in the positive direction x, this 373.3 watts is flowing per meter square. So which area is this? This is the area here. It's over this meter square per unit of that area. So heat is flowing this way, but per unit area the value is here. Then instead of skin plus fat, suppose, which has a lower thermal conductivity, by the way, if we have a muscle which has almost twice the thermal conductivity. In other words, skin, the fat is kind of an insulator. That's the main point here. So if it is muscle, then I plug in, instead of 0.28, 0.56. Otherwise, the same numbers, and we of course get twice the flux. Okay, so if I know temperatures at 2 points, and we happen to know that it's a straight line, so we know the gradient or the slope, then we can find heat flow. So of course, we need to know the thermal conductivity. Now, the fact that heat flows from hot to cold in this direction and a certain amount, this physical answer should obviously not depend on which direction I chose x. So if I choose it this way or this way, my answer should not change. So this is not the way I'm choosing now. So let's redo the problem choosing my x direction as an opposite direction. Before it was this direction, now I'm choosing in this direction. And let's do the problem and see how things work out. Okay, so I'll just do the first part, the skin plus fat with a lower thermal conductivity, and we have the same formula. The meaning of the formula again is this gives me heat flow in the positive x direction. So my positive x direction is this way. So whatever I get here, that would be heat flow in the positive x direction. So if I plug in the numbers, this time minus k and then del t, I'm going this way. So the point ahead is 20 minus the point behind, 20 minus 5 divided by 50 times 10 to the minus 3 is equal to minus 373 points. So we did not get the same answer. If you recall the answer, or if you look at it in the text, this answer for the first time around was plus 373. we got it negative here. Does that mean we get two different answers if I choose my x direction differently, and does that change the answer to the physical problem? Of course not. So what is the meaning of minus 373? Uh, so that means heat flows in the positive x direction to the tune of minus 373, which means heat really flows in this direction. So we are consistent with the previous formulation. So thermal conductivity, as introduced in the last couple slides with the symbol K, how much does it vary? It of course is a measure of how much the material conducts heat. So this capability to conduct heat, how much does it vary from one material to another? Is there a big picture? We're not going to, of course, try to memorize thermal conductivity, but can we get an overall understanding? And that comes this way, that gases which are rare, the molecules are farther apart, these are the least efficient in terms of conducting heat. On the opposite end are solids that are dense, and the molecules are closer together, so they can conduct heat a lot more efficiently. On top of that, some of the solids, the metals, have free electrons with them. Now the free electrons are also, they're mobile and they can also carry energy. So these also add to the these materials being higher conductivity. So let's look at some real data. So gases, for example, carbon dioxide to hydrogen, they are in the lowest range, the lowest values of thermal conductivity. So this is my K, and here are the gases. And the solids are on the higher side. This is non-metallic solids, and you can see the values are, you know, this is 10 times 100, it could be 100 times, or even 1,000 times almost higher than the low end of the gases. Um, the metals, which are solids plus they have free electrons, that are even higher. So they are really high thermal conductivity. Okay. So the big picture is gases on one end and the solids on the other end. Now let's have some even more specific information on biomaterials. So we can think of biomaterials at, the different states covering a large range of possibilities. And we're talking mostly plant tissues and animal tissues. So if the material is all dried, normally they have lots of water. So if they're all dried, then the water gets replaced by gases, by um, water vapor, by just by air. And so a dry and porous biomaterial will have the lowest of the thermal conductivity. A wet biomaterial will have higher values because the pores are not air of low thermal, but water. Now, a frozen biomaterial, that water gets replaced by ice, which is a solid. So as you can see, ice as a solid has higher thermal conductivity than water. So biomaterials, when they go from wet to frozen, then K should increase. So a frozen material would have higher thermal conductivity. So it's good, it's very useful to have this qualitative picture of where these thermal conductivity values stand. Once again, gases are the lowest and solids are the highest and liquids are in between. Now this thermal conductivity that we keep talking about, let's spend just a few minutes looking at where does it come from? Is this something from theory, or where does it magically come from? Is it a fudge factor? You know, it is measured most of the time. And here is a simple measurement probe. So think of this as a stainless steel or other high conducting material metal sheath. Okay, so it's a metal sheath inside which we have a electrical heater. So this is connected to battery, and that generates heat. As it generates heat, that heat is it's going to make this sheath hotter, and depending on what material I insert the sheath into, the heat that is generated is going to dissipate into the material easier or faster, easier or slower. So if it is a highly conducting material, then heat from inside is going to quickly get out. On the other hand, if it is a very insulating material, then heat cannot get out as easily. What would be the result? When heat cannot get out as easily, then all the heat here is going to raise the temperature in here easier than the case when it's highly conducting outside, so heat can leave more easily, and therefore the temperature in here would not rise as much. So how the temperature rises in here is a measure of what is surrounding this probe. Therefore, if I measure these temperatures, then I should be able to say what is surrounding this probe. In other words, what is the material property. Okay, so the relationship between the heat generated and the temperature rise is given by this equation. So this says at time t1 I measure temperature T1, and at time T2 I measure temperature T2. Then those two temperatures are related to these two times this way when we know Q. Now normally you'll see that we would do a lot of problems where our goal is to get temperature as a function of time when Q is known and thermal conductivity is known. Here we want to do the inverse of that prediction of temperature. Here the temperature, instead of predicting, I'm going to measure using what is called a thermocouple, as we have already talked about. So we insert also a very thin thermocouple inside the tube, and we actually measure these temperatures at the two different times. So we measure the temperatures and we know how much heat we are putting in. So everything is known other than K, so we find K. So then K comes from this kind of measurement. It's almost always measured for real material. So thermal conductivity then is a measured material property that is measured using probes such as this one. So time for a little quiz. So if we think of a biomaterial to be made up of the ingredients, which would be some solids like the proteins or carbohydrates and water or ice, plus some empty spaces, air. So if we think of biomaterials this way, can we try to predict what would be the thermal conductivity of the same tissue in this case? These are chicken breast muscles, and what are they going to have the same property at the three different conditions? One is frozen, other is just regular uh, breast uh, meat that is at room temperature, and this one is freeze dried, which means it's frozen and then dried, so all the water is first converted to ice and then it's sublimated, so it's gone, so there is no water in there or very little water, so it's dry. So are they going to have the same thermal conductivity? So at this point, you should pause the video and take 2 minutes to think about it. For now, I will give the answers. So at the frozen state, there's all the water has turned to ice, so there's a lot of ice, so its thermal conductivity is the highest. Okay, then at the at the dry state, the thermal conductivity is the lowest because all the water here got replaced by air that is much lower thermal conductivity. Okay, in between is this one where it's not ice, which has a higher thermal conductivity, but it's water. So this value comes out to be something like 0.47, something like that, closer to the property of water. So frozen, the highest, then uh, unfrozen, but water is in between, and the dried is the lowest. So you notice it's the same biomaterial, but its property depends on obviously the state or the composition of it. Another characteristic of thermal conductivity is that as temperature increases, thermal conductivity increases. So this is thermal conductivity and it increases with temperature. We can see this with real properties, in this case of cow liver. So which would be quite representative of other tissues. So quite often you see this thermal conductivity increasing with temperature. So that's the first point. Um, the other point is to remember that it is a biomaterial. So suppose you heat beyond the point where the proteins are denatured, so you heat to much higher temperature. Then you have changed the material. So when you heat versus when you cool, and then you bring back to the same temperature, you don't get the same thermal conductivity because now the material is different. Its composition has changed, its structure has changed, so it has a different property. So biomaterials can get changed in an irreversible way with temperature because the material itself changes. Notice here we didn't go to as high a temperature, so heated versus cooled, you get the same thermal conductivity. Not so here. Okay. Now I want to just mention this other property called thermal diffusivity. You recall the heat equation looks like this, right? If I have no convection, no heat generation, then it looks like this. So del T is K over rho Cp del square T del X square. So quite often in transient problems, we will have this quantity K over rho Cp together this way. And this has a very special meaning and it can be physically interpreted. So for now, we are going to interpret that actually later on, but for now, this K over rho Cp has the unit of meter square per second and it's called thermal diffusivity. It is actually analogous to mass diffusivity. Many of you know of just molecular diffusion processes, mass diffusivity. This is very analogous to that. Like mass diffusivity measures how much things have moved, so thermal diffusivity measures how much is the energy front moved. Okay, so higher thermal diffusivity means the energy front moves more easily. Okay, as I said, more on this is going to be discussed later. Okay, we're finally done with conduction and we move on to convection.
To recap, conduction in a gas, for example, refers to this kind of molecular motion where the red ones, for example, have more energy, and as they're bouncing against the blue one, it's transferring energy. Contrast this with convection, where on top of this molecular motion, we have bulk motion. Notice that during the bulk motion, this random movement of the molecules did not get stopped. So the bulk flow is on top of the random molecular motion. In other words, we can think of convection as conduction plus the bulk flow effect. We're going to study convection in a lot of detail. So we have an entire chapter dedicated to that. So now we just get a quick formula that actually we have seen, probably many of you have seen that in high school, but we need the formula to do other problems until we do the convection chapter. So that's all the purpose of this slide is. So we normally divide convection, the study of convection, into natural and forced convection. Now, what makes it natural convection? So let's look at this example where we have a warm part of body, it's a hand, and that surface is, let's call that as surface 1, which is warmer than the surrounding fluid temperature 2. So what will happen is the air right next to the or touching the hand will get warm first, and warmer air will expand, so it will get lighter, and because of gravity that will start to go up. So there is going to be a bulk flow that will happen because of this temperature difference and gravity, and so that is happening very naturally. So that's why it's called natural convection.
The other one is forced convection. Um, and forced convection, we have something like a fan, for example. Sorry about my drawing there. A fan blowing is going to cool you down, for example, or okay. And so here the surface, the skin surface is 1 and the fluid is 2. So there is heat transfer between the solid surface here and solid surface and the fluid one way or the other, and that amount of heat transfer is what we're after. The mechanism here is the fluid gets heated by the surface and then the hot fluid is removed by this forced fluid flow. Now, both of these processes would be studied using one simple equation that says that the flux is equal to some convective coefficient that depends on the situation, whether it's this or this, it depends on those, and the temperature difference between surface 1, here, surface 1, for example, in natural convection, or surface 1 here in the forced convection case, between surface 1 and fluid 2. Now, like all heat fluxes, this has a direction that is very important to keep in mind. It's from surface 1 to fluid 2 when you write it as T1 minus T2. So when you write T1 minus T2, then this heat flux is happening from 1 to 2.
Now let's get back to this direction of this heat flux in case of convection. So this formula that we wrote, Q double prime 1 to 2 is equal to H times T1 minus T1 minus T2, temperature difference between surface and fluid. We don't have to worry about which one is hot and which one is cold. Now you might say, oh, that's crazy because heat can only go from hot to cold. So why wouldn't you be concerned? The way we have written this formula by taking difference between T1 and T2 and calling the heat goes from 1 to 2 automatically takes care of this. So let's see. So suppose we have a body, a solid with temperature T1 and a fluid with temperature T2, then there are two possibilities. One is body 1 is hotter, and so the temperature difference in this equation T1 minus T2 is positive, and therefore in this equation you'll get a positive heat flux. So which means heat flows from 1 to 2, and that is thermodynamically consistent because we said T1 is higher than T2. So heat should flow from T1 to T2. That's what we get from the formula. In the other situation, fluid 2 is hotter, so the solid is colder. So if I use the formula here, then the temperature difference T1 minus T2 is negative. And if I plug that in here, then I get a negative heat flux. So Q1 to 2 is negative. So what does that mean? That heat flow from 1 to 2 is negative. That means heat really flows from 2 to 1. And that is again thermodynamically consistent because we said this in this case T2 is hotter, so heat should go this way. So the point to make is when we write this formula and decide on the direction, we don't need to know which is hot, which is cold. As long as we write T1 minus T2, body temperature of body 1 minus temperature of body 2, and say that whatever we get is the heat flux from 1 to 2. If we follow this convention, then we will always be okay. We'll always be thermodynamically consistent. We don't need to be concerned about which one is hotter and which one is colder. So we now want to simply apply that convection equation. No big deal, just putting in some numbers. So we want to calculate how much heat would we lose from our body to the air. Now such heat losses are extremely important for our thermal comfort, and they're measured using mannequins like what we are showing here. So heat flow from body to air would be equal to H times T body minus T air. Notice I don't need to know if this is hotter or this is hotter. We just write T body minus T air and say that is the heat that flows from body to air. Now we multiplied this by area because it is not flux, but it is over the entire surface area. So if H is given as watts per meter square per degree centigrade, which by the way is the unit for H. So H is in watts per meter square per degree centigrade. You can contrast that with K, thermal conductivity, which is watts per meter per degree centigrade. Okay. Times again our typical body surface area 1.4 meters square, and the body surface temperature taken as 37, and air temperature as 20. If we plug that in, we get 119 watt. So the meaning of this is the amount of heat that we are losing by convection under these conditions. Whatever condition led to the H equal to 5, as I said, we will spend the whole chapter on seeing what H means and how do we find it. Okay, finally we move on to radiation, and again we have a whole chapter on radiation. So what we will do here is a very simplified version of the radiation equation. So we talked about conduction, that is by contact. Energy is transferred by contact. Then convection was a flow, bulk movement on top of the contact. Radiative heat exchange is fundamentally different. It is in the form of electromagnetic waves. We do not need any medium, meaning we do not need a solid, liquid, or gas. Energy can move simply in the form of electromagnetic waves, and everything emits these electromagnetic waves. All material above absolute zero emit this radiation. So how much is emitted? If I think of an area a body with surface area A at a temperature T1, then the radiative heat flux, which is radiative heat flow per unit area of the radiating surface, is equal to some universal constant which we will be calling Stefan Boltzmann constant. Boltzmann constant, and times the absolute temperature. So higher the temperature, more is the energy radiated. And it's radiated for an ideal body, it is radiated in all directions. So let's plug in number and see how much we radiate. So the amount radiated by us is this constant times our typical surface area times the absolute temperature of our body surface, not the core, the body surface, raised to the power 4, that gives 697 watts. Now that seems like a lot of energy that we are leaving. There is a bit of a problem with that. Can you guess? Yes, we are losing this quantity, but this is how much we will lose if we are naked in space, so that we're not getting back any radiation from anything. Um, in reality, when we are on Earth, then whatever surrounds us also is radiating back to us. So if we are one, then the surroundings, anything around us is also radiating back to us. So we are radiating to the surroundings and the surroundings are radiating back. So we need to think of a net radiative exchange between these two. And the net exchange formula is, of course, different. And so now radiative heat flux is equal to this body's temperature T1 minus the T surroundings temperature, which is kind of, you can guess that because this is it's getting back this amount. We will have an entire chapter for radiation where we'll go through most of these details. So for now, using this simple formula, let's get a realistic estimate of how much heat we are really losing. So again, our body surface temperature minus, let's say, surrounding temperature, 20 degrees centigrade. That's not a bad assumption for the walls around us. If we plug that in, we get a much lower number of 111 watts, which we would be losing by radiation. We will see that losing heat by radiation is an extremely important part of our thermoneutrality. To summarize then, we have talked about three different modes of heat transfer, and for each one we have a little formula. But before that, conduction is through physical contact, and then convection is bulk flow added to the physical contact, whereas radiation is fundamentally different. It does not need any physical contact or no medium needed. Okay, now conduction is the rate of heat transfer by conduction is given by this Fourier's law, and for each one of these formulas that we will see, you can see three of them, they all have the fluxes, they have an implied direction. So if you use this formula written as it is, minus k del T del x, which is the way we would always use, the heat flow is in the positive x direction. And this k is the material property that we need to know. Likewise, in convection, if I write the equation this way, then the heat flow is from 1 to 2. So that is the direction. We don't need to know which is hot, which is cold. It will work out. And then convection is characterized by this H, which has the flow effect on top of conduction. Conduction is still there. Okay. And then finally, the radiative equation, again, the heat flux is going from 1 to surroundings. So we could say 1 to surroundings. So it also has an implied direction. Like here it's from 1 to 2. Here it is from 1 to surroundings. So they all have directions, and um, and then this is now the rate law. Remember, we were missing a rate law that says how fast things are happening. So the units for these is the fluxes are watts per meter square. So, or joules per meter square per second. So now we have a law that says at what rate heat is moving per unit area per unit time. So this is going to now tell us how fast or how slow does the process happen.